Morning. I'm very happy to be here to try to give you some more information on fracturing. It was mentioned that I started in 1974, and I got a little story to tell you about that when I kind of stumbled into fracturing. You know, I wasn't a fracturing engineer back then. I was a sand control engineer out in the field. So I had to help the operator convert a producing well into a water injection well. And we had to put in what we call a sand control process to put sand down there to keep the water injection under control. And the operator gave me a lot of data that I had to look at to design that operation. And when I got through with it, I went back and I said, you know, the fracture gradient is so low that while we are injecting this slurry of sand, kind of like a frac fluid, we're actually going to fracture this formation to a small degree. And he said, no problem, let's go ahead and do it. And I said, well, I need some more sand out there, so we ordered some more sand. And get out there and do the operation, and everything went as planned. The big difference was that the next morning they woke me up. This was an offshore rig, so I was sleeping out there, and said, hurry up and come quick to this wellhead. You know, we've got pressure on the wellhead, which was not supposed to be any pressure on the wellhead. That means that the producing tubing that was in place had pressure inside that, just like you would have on a producing well. So I said, oh my goodness, since this formation was depleted of oil production, there shouldn't be any there. And we need to sample it, so we sampled it, and it was very good oil. And instead of being the brine water that was in place when we started the operation. So I said, well, let's put it on production and see what it'll do. And it turned out to be the best producing well in the entire area. And so what had happened was that the small fractures that we had put in the formation down there in the producing zone had bypassed some damage to the permeability of the rock that had prevented the oil from being produced. And based on the data, you couldn't tell the difference between a depleted zone and one that was damaged at the time. We didn't have the right kind of data for that. So it kind of gives you an idea that you can do a lot of different things with fracturing. Besides shale, we've been using it for those particular operations in sandstones for decades without any problems. So let's get started and look a little bit more into the shale fracturing. A few years ago, we formed an ad hoc committee we call the Well Completions Committee for the fracturing operations, well construction, and integrity guidelines. And this document was put together in a few months, mainly to give an overview, summary, of what we are doing out there in the field for fracturing. It focuses on well construction and integrity in order to make sure that we have isolation of the hydrocarbon zones with the well construction and the cement. So on this diagram here, we typically have the types of casing. The black here is the casing strings in the well. Start off with the conductor, which is a short one up here at the top, and then go to surface casing. The unique thing about that one is that most or just about all of the groundwater is supposed to be isolated by the surface casing. And that would protect that's the main line of protection for the well to prevent any issues with groundwater. Next, in some cases, the deeper wells have an intermediate string, and then finally a production casing string, or in some cases a liner. And in all cases, those strings of pipe have to have cement. And that is to make sure that the drilled hole and the pipe annulus, in other words, the space between the pipe and the hole, is filled with a material like cement that prevents fluid from formations migrating up or down into places that it should not go, like groundwater zones. Now, when we design the casing program, there are a lot of complex calculations that we do to make sure that all of the loads that are encountered, including the fracturing pressures, are going to be contained within that casing. In other words, we're not going to have a leak in the casing. And that we have API standards. For example, we have the API 5TC for that, to tell the manufacturers the specifications that we'd like to have in the casing. And here we get into the cementing operation. And the diagram we have here kind of represents what's going on with the pipe in the hole. This is a cementing mixing and pumping unit here, usually on a truck. Offshore we have skid units. And this is the rig. So as you saw in the video, we're mixing and pumping cement through the line here and into the wellhead, and it's going down the inside of the casing. Now, what we do first is to launch what we call the bottom plug. That's a wiper plug that separates the fluid ahead from the cement so that we won't contaminate the cement. And then we follow that with a top plug. So the cement is in between two what we call rubber wiper plugs, so that the fluid ahead and the fluid behind do not mix with the cement and dilute it and make it where it won't do its job. So we pump the displacement fluid behind the cement, and this plug will end up down here at the bottom, kind of like this one here, where the plug will seat on the bottom plug and prevent any further movement of the fluid inside the casing. And there's a little pressure increase, and that's a signal that the cementing job has been completed. And then we test it here. We usually have the float collar and float shoe down at the bottom. We'll open the pressure here at the top, release a little bit there if there's any left, and look to see if we have what we call any flow back from the inside of the casing out, which would indicate there might be an issue that we have to address. In the great majority of all the cases, we don't have those issues. I wanted to mention that a little bit later we're going to have a discussion on Standard 65, Part 2, and that'll give you a lot more detail on this operation. Next we have the logging operation and testing. And this is where we do logging in the open hole before we set the casing. And in many cases we do also logging after the casing is set for particular data. That would include what we call an MIT. That's a mechanical integrity test to make sure that we can apply pressure to the inside of the pipe, and we'll watch that pressure for a given amount of time to make sure there's no leaks. And then there's LOT, that's a leak-off test. And that's where we do a similar test, but it's to test the formation to hold pressure instead of the pipe. And that is those two tests are the primary pressure tests that we do to look for any issues with well integrity. And again, the great majority of those tests that are run are very successful and they hold pressure. If some of them don't, we have remedial practices that we can apply to make them hold pressure. And a lot of the cement evaluation logging information is in this API publication, 10TR1. And that includes ultrasonic noise, well, it does not include the ultrasonic noise logs or the pulse neutron logs, which are run later to identify if there's any fluid or gas that's migrating behind the pipe. And if we do find it there are remedial practices that we can implement to stop that and regain the zone isolation that we need for the integrity of the well. So some of the key factors that we look at for each casing that we set. For example, the conductor casing will hold a lot of the mechanical devices that we have in place, and it will also serve to isolate shallow groundwater zones. However, the main one for the protection of the groundwater is the surface casing, as we mentioned earlier. Next, the intermediate casing, that isolates formations which are usually not going to hold some of the pressures that we'll have for the rest of the well. So we isolate those formations with an extra string of casing that will hold those pressures. And then, of course, the production casing was designed to hold all of the load pressures that are going to be applied to the well during the construction phase and later on during the producing phase, including the containment of the hydraulic fracturing process. So when we get into horizontal wells, which have been around for about 30 years in a number that we would think is significant. Before that, it goes back another 50 years where we've experimented in the industry with horizontal wells, but they never did really catch on. So back in the 70s and 80s, when a few operators decided to try horizontal wells on certain conventional formations, let's call it, which are the sandstones, they saw very good improvement because they were able to get a longer drainage area in the formation than you would with a vertical well. And as you can see here, if we're vertical, we don't have much length of exposure for the reservoir to drain into the pipe. Whereas here, we really have a substantial longer distance for that reservoir to produce into the pipe, which makes a lot of difference in a lot of formations. What we found, let's say in the last 10-15 years, is that when we put in shale formations, is when we put in small hydraulic fractures along the length of that horizontal, we further increase that drainage area, and I'll show you some more slides here in a little while to get more detail on that. One thing to mention, though, is that for certain wells, we don't put casing here. We go with what we call an open hole completion. And in some areas, that is very practical and very efficient and still will maintain zone isolation because we have the pipe all up here to the surface with all those other strings to maintain zone isolation to keep the reservoir from producing into groundwater. When we do the perforating operation in a cased hole, we are creating a hole into the pipe so that the rock in the formation can have communication with the inside of that producing casing. And that is an operation that can be done in several different ways, but the most common one is to have what we call a perforating gun that has an explosive charge that's actually a shaped charge that when it ignites, it has a tremendous force that will actually punch a hole through that steel pipe and some distance into the rock. It also goes through the cement. And what's left is what we call a perforation tunnel. So you can see we have several inches of drainage area for that rock to produce into the casing. So when we do hydraulic fracturing, which as we mentioned earlier, has been done a very long time. The first one there in 1947. We see in almost all cases a very great increase in this exposed area for the reservoir to produce into the well. And in most cases it's high conductivity. That means that there's a lot of permeability. But in the case of shale, it's a low permeability. In some cases it won't produce at all with some fractures. And you have to get special fractures, to make it really produce well. And that's what was shown a little earlier, where you have to have multiple fractures, and when the multiple fractures go out into that rock, they are either going to intersect natural fractures in the rock or make other fractures that will increase the drainage area into the rock and then into the well. So if you look at a vertical well from the top down, this is the exposure you have to all of this surrounding rock. And that is not very much when you compare all of this on a horizontal well or a fractured well that's vertical. So when you put this type of drainage area all along that well, you can see that there's multiple increases in the exposure, which really improves the drainage. So we have to get up to pressures that will actually crack the rock and separate that fracture wide enough so that we can get sand or other proppants into that crack, because after we release that pressure, the rock is going to close. There's very few cases where it stays open without proppant. In most cases, we have to have that proppant in there so that when it closes, that proppant has a permeability that's going to stay there that will give us the drainage flow path into the main part of the well. And we propagate. That means that we try to penetrate to an optimum distance away from the casing so that we get a defined amount of drainage area that computer programs can predict the actual increase in production from that. So why do we do this? Obviously we just explained some of the reasons. We crack the rock, we increase the drainage area, we get higher production for a single well. And the cost of doing the fracturing operation is, in almost all cases, less money than drilling another well. So when you do it in hydraulic, when you do the hydraulic fracturing in the horizontal sections, in some cases we see each one of these fractures producing what a single vertical well might produce. And so there's very cost effective to drill a few wells horizontally and get the production that you would have with a great number of vertical wells. So let's get a little bit more into the science behind this. One of the things that happens is that when you apply pressure in a shallow well, the fracture may not look like you're seeing in most cases. It actually may have the shape of a pancake, which means it's kind of spread around in what we call a horizontal fracture plane instead of a vertical fracture plane off of the casing. And that's because of some stresses that are involved in the rock, the overburden stress, versus the stress that it takes to, or the stress that's you have to overcome with the frac pressure in order to crack the rock. And we call that least principal stress. So I'm not going to get too much into this science here, but it's something that we can measure and we can calculate. In a lot of cases, we do the measurements before we apply the big fracturing operation. In other words, we do a very small, what we call a microfrac, that will give us data in order to calculate these stresses, and that will allow us to fine-tune the fracturing operation to make sure we're putting the right size fracture in that well. Now, the other main type that we go after, in other words, we're not trying purposely to do this in most cases. In most cases, we're trying to get what we call a vertical fracture plane. And that means that the stresses are different, and that we can achieve that. We can actually measure it before we apply the fracturing and be sure that we're going to have this happen. And so we can predict that and again, calculate the increase in production that we'd have with a series of these types of fractures in the shale.